Diffusion, we're talking about diffusion in fluids, gases, and liquids, right? And what we're really going to be talking about is how molecules are moving. Molecules are constantly in motion, and there are two types of motion that we want to separate out. One is self-diffusion, right? And the other is a concentration gradient driven diffusion, right? And we're to describe these motions of molecules, we'll talk about flux. Flux is the motion of something through a unit area per unit time. And we can have different fluxes, right? There can be matter flux, that's number of molecules moving through a square meter per second, or we could do that in terms of moles, right? Energy flux, that's joules going through a particular unit area per unit time. All right, so there are different fluxes. Here we're going to be talking about the fluxes of molecules, moles or number of molecules. Right? Now at equilibrium, the composition of a solution, for example, or a gas phase, liquid in a container, right, that has to be uniform everywhere. If there is a concentration gradient, then there is a chemical driving force. We'll call that the chemical potential. There's a chemical driving force that pushes the system to randomize and get that uniform concentration. The chemical potential, you can think of that as a gravitational potential, right? If you take something and drop it, you know it's going to go to the floor, right? Same way with the chemical system, it always wants to go to the minimum of the chemical potential, right? So diffusion is that process that transforms a non-uniform, non-equilibrium concentration profile into an equilibrium distribution. But also, even at equilibrium, the molecules don't stop and they keep moving around, they keep colliding with each other. So if you looked at any molecule, it would move all through a container, right, in a fluid. And that's what we call self-diffusion. But at equilibrium, there's no net flux of material. Concentration gradient will lead to changes in how matter flows, right? It flows from high concentration to low concentration until you get to that equilibrium distribution. And the rate of diffusion, it's proportional to a concentration gradient. A concentration gradient, right, dc dx, how the concentration changes as a distance, x in this case, right? And the proportionality constant between the flux and this concentration gradient, right? The bigger the concentration gradient, the bigger the flux is going to be due to diffusion. The proportionality constants for that are the diffusion coefficient, D, and the area, right? A flux, again, is just in this case, our flux is matter flux, right? The change in the number of moles per unit time. D, what's D? This diffusion coefficient. There are several ways we're going to discuss what the diffusion coefficient is and how you can get at it, right? One way to define it is it's related to the mean distance a molecule travels between collisions, right? The mean free path. We introduced that last time, lambda. And if you take lambda, the mean free path, times the mean velocity, that's that v bar there, 1/2 lambda v bar, that would give you the diffusion coefficient. All right, so that gives you one physical interpretation for the diffusion coefficient. Flux of molecules, right, is related to the concentration of those molecules times their drift speed. The Einstein relation, you connect the diffusion coefficient to the friction coefficient, right? So larger friction in a sample, smaller diffusion coefficient. That kind of makes sense. In a system that has a charge on it, charge Z, right? You can relate the diffusion coefficient to that charge and the limiting molar conductivity. So diffusion is one way you can move around charge in a solution. In this Stokes-Einstein equation, you can relate the diffusion coefficient to the viscosity of a liquid. That's eta down here, right? And R, which is the radius of the molecule. Bigger molecules have a smaller diffusion coefficient. Kind of makes sense. More viscous solutions, smaller diffusion coefficient. How does diffusion change the concentration gradient? How does the concentration gradient change as a function of space and time? And that's given by Fick's second law. So imagine we have a system at time t equals 0 where we put all the molecules on the wall of the container, right? Initially at t equals 0, everything is at x equals 0 on the wall of the container. In infinite time, what we are going to get to, right, is a flat distribution, the concentration, right? We've got concentration over here on this axis. The concentration will be uniform once we get to equilibrium. What does the concentration profile look like in the meantime? Well, it starts off everything on the wall. It's going to end uniform. And in the meantime, you get this nice smooth curve, which is an error function. An error function that looks a lot like a Gaussian, right? A bell curve. And so at short times, right? And really it's the diffusion coefficient is going to help us set the time scale on this. So it's a short product of time times the diffusion coefficient, right? Most of the molecules are close to the surface, but a few of them are able to move quite far away. Not all the molecules move uniformly across the whole container. They move to fill out this sort of half of a bell curve. All right. And so as time progresses and we go further and further, the concentration near the wall where they all started will go down, and the concentration far away from the wall will go up as the system evolves from a non-equilibrium distribution to the equilibrium distribution where they're uniform across the entire container. Now, the root mean squared displacement, right, that a molecule goes through is related to the time we wait, that's T, and the diffusion coefficient, right? The longer we wait, the longer molecules will be able to move through diffusive motion. And that root mean square displacement depends on the dimensionality of the system. We could have two-dimensional diffusion. That's when molecules just diffuse on a surface. Three-dimensional diffusion, that's when molecules get to move through an entire beaker, for instance. How can we relate the diffusion coefficient to the mean free path? One model for that is known as the random walk or drunken sailor problem, right? Where what's going on is the molecules are moving around. They have thermal energy, right? Translational energy. They're moving around in random directions. Bam, they collide with the molecules next to them, and then they scatter into a different direction. The time between collisions, we'll call that tau. The distance between collisions, the mean distance between collisions, we know what that is. That's the mean free path. And indeed, in the Einstein-Smoluchowski equation, we can relate the diffusion coefficient to the mean free path squared divided by 2 tau, the time between these, right? So that's a nice physical idea behind the diffusion coefficient, that it's related to the step size, the mean free path, and the number, the time that it takes to make a step, right? The time between collisions and the mean distance between collisions, right? And the mean free path is related to the size of our molecule. If we had hard spheres with a diameter of sigma and a number density n, right? The mean free path, the bigger the molecule, the smaller the mean free path, the higher the density, the smaller the mean free path. So in liquids, it's really small, whereas for low pressure gases, the mean free path can get quite large.